So now that we have a better understanding of different notations of the different parameters in the neural network, we'll move on to our previous discussion, the very previous discussion where we discussed about what are all the mandatory things which we need to specify for a given neural network. So we had six main things to define for specifying a neural network. That is network topology. That's we have covered already. Input layer, we have covered it. Output layer, we have covered. Weights, biases. So all these things are done as of now. So the only thing we are left with would be the activation functions. In general, we have already discussed about activation functions. That is, we have two different kind of activation functions. That is a logistic or a softmax function and a binary class classification or uh, a network based on a network topology. That is identifying a one common solution. Then that would be a sigmoid function. So we will have a set of discussion on this activation functions basically. So when it comes to parameters and hyperparameters of a neural network, we pretty much know about the parameters which we involve in a given neural networks. That would be weight, biases, inputs, outputs, etc. But we have certain things called as hyperparameters. That is the number of neurons in a given neural network in a particular layer, number of hidden layers, number of uh, layers between them, etc. So these would be a tuning parameters, what we call the hyperparameters or the decision taking parameters, which we take by performing certain trial and error on our neural network. So in that scenario, or generalizing on a hyperparameter, activation function, the selection of activation functions would also be a hyperparameter, would also be a decision taking parameter that we have to decide when we design a neural network. So what exactly we expect from a activation function? We know that as a ground rule, we know that the activation function will sit in the output layer, right? So the output layer, there will be a activation function. What would it would generally do? It will generally apply certain function on cumulative summation of the input signals, right? That's all it will do. The function or the mathematical equation which it applies on that particular summation would be different based on the different scenarios. But on a whole, the expectation of a activation function sitting in the output layer would be to apply certain mathematical equation based on the scenario on the summation of the different input signals, right? So what general characteristics we will be expecting of a ideal activation function to be? So the very first thing would be activation functions should be smooth. That is, they should have no abrupt changes when plotted. So what does that mean? Let's have an example for that. So here is a curve which I am representing. So this is a one activation function. That is there is no mathematical equation, but consider this as a activation function. What does it show? So for all the values from 0, 1, 2, 3, 4, 5, the output signal or the output or the mathematical equation output is just 0. For input 0 equals to 0, 1 equals to 0, 2 equals to 0, etc. But whenever the x values arrives at 5, suddenly there is a high pitch, or suddenly there is a frequency output, what we can see at the input equals to 5. That is, for x equals to 4.999, the output is nothing. It is dormant. It is still showing 0 as a value. But as soon as you give a signal with a value 5.001, there is a sudden jump in the output signal, that is 20. So this is what we call or we iterated on this point, that is activation function should be smooth. They should have no abrupt changes when plotted. So this is a clear non-ideal activation function. So generally we don't expect any activation function to behave in this way or in this manner. So it should be very smooth. That is, it should be in other words, what we can say, it should be considerate amount of input. There should be a considerable amount of changes in the output as well. So there should be going hand in hand instead of a just abrupt changes. See, suppose I want to know the output signal for an input say 4.5, then I would be just getting it 0 right over here. But that would not be the thing. It should be a smoother curve, almost a smoother curve. So for any little changes or minor changes in the input signal, there should be a certain amount of deflections or signal variations in the output as well. So the second point over here would be they should also make the inputs and outputs non-linear with respect to each other to some extent. There shouldn't be a linear curve. Even if I plot this as from starting from the origin, if I just start plotting the points of input and output, if I just get a straight line, then that would not be also a behavior of an ideal activation function. For a given input, if there is an exact value, that output that can be predicted, or there is an definite output providing for that given input, for 5 as an input, if there is an 5 as an output, or like certain some linear variation dependency between the x and y values, then that would not be also ideal characteristics of a activation function. So there should be a non-linear dependency or non-linear correlation should be present between the inputs and outputs when we plot the activation functions output versus input curve. So this would be the two major characteristics which we expect out of activation functions. So, keeping these 2 points in mind, we have certain popular choices for activation functions to be. The number one choice would be the most popular activation functions used for the neural network are the logistic function, that is softmax. So we already studied this equation in the previous sessions, right? So this logistic function or the softmax function would generally approach or generally applicable to the task of multi-class classification, right? So we'll be generally expecting this kind of scenario in a real world, right, where we have to classify the input signals into different classes, different output classes, right? So these are all the scenarios which will be generally expecting in the actual real world. So that's why this would be the most top or the most popular choice when it comes to activation functions. So you can reiterate on this equation as well. So the logistic regression for P naught or the probability P0 would be represented as e power W naught into X dash, since we took same input signal, divided by e power of W naught into X naught X dash plus e power of W1 into X dash plus e power of W2 into X dash. So this is how a generalized equation would be looking like for a number of inputs and outputs and the weight associated with it. So this is one of the top choice when it comes to activation function. Then we have a sigmoid function, that is the second topology, that is identification of one common solution, whether it is an yes or no, whether it is true or false, or is it right or wrong. So in those kind of scenarios or the uh, general scenarios where we approach this sigmoid function uh, on top of logistic regression, right, or a logistic function. So the sigmoid function would be a what we can call it is a sophisticated form or a iterated form or a purified form of logistic function. Here in the logistic function, we would try to have a classification of multi classes, but we have only one class to be determined. By knowing the probability of the output of one class, we'll automatically detect the probability of the other class. So that's where this sigmoid function will come into picture for the activation function, and it is generalized as 1 divided by 1 plus e power of w naught minus w1 into x dash. So the x dash represent a same input signal throughout the neural network, or we can call for a given output signal. This is how we define a sigmoid function. When we plot that, this is how a general sigmoid curve would be looking like. As the name indicates, it's a sigmoid. This is where the term originated because of the nature of the curve it is. So it is a S-shaped sigmoid curve. It would be a general smooth curve for a particular input for taken at any scale. Say if it is a minus 4.23, 4.44, etc., we still have an output signal detected, right? It is not a abrupt change in the output signal. So that's what the characteristics of a activation function should be. So there is a smooth curve which we could see for this particular sigmoid function. So moving on to the other popular choices, we have hyperbolic tangent function, where it uses a tan hyperbolic function in order to determine the or calculate the output of a given neural network. So this is how it is represented as e power of x minus e power of minus x divided by e power of x plus e power of minus x. This is a general tan hyperbolic equation which will be applying on the cumulative sum of the input signals. And when we try to plot that, it is almost similar to the sigmoid curve, but with a higher altitudes, right? So the length of this would be more when it comes to tan hyperbolic tangent function or hyperbolic tangent functions. Then we have another last but not the least popular choice, that is rectilinear or rectilinear unit function. It is it is some more popular, or in the recent days it is becoming more popular to be using this as a activation function in the large structured or a composed or a large neural network when it comes into the picture. So the rectilinear output or the rectilinear unit function output would be in this way. So for x greater than 0, x greater than 0 equals to, it will be a line, right? So it will be reacting or it will be giving a certain output. But all the otherwise, if x value is less than 0, then the network remains dormant, that is 0. So this is how a rectilinear unit function would be looking like. For all the values of x, if the x value is greater than or equals to 0, then it will be there will be a changes in the output signal. But otherwise, if it is less than 0, if the x value is less than 0, then it will be 0 again. So there will be no changes in the output. So these are all the popular choices of activation functions. So by this, we have completed how we build neural networks or artificial neural network inspired from a actual human brain, and we summarized certain takeaways from the human brain, and we structured our artificial neural network with the concept of perceptron. Then we understood different parameters associated, different topologies, different hyperparameters, and finally we have ended up with activation functions as well. So by this module, we would have been very got an idea about what artificial neural network will look like, and would and how would be the approach when we build a artificial neural network. Thank you.